A little more of an English lesson. Here we go. Perpendicular lines. So perpendicular lines are two lines that make a right angle. So you've worked with perpendicular lines before. Two lines that make a right angle. And the definition for a line perpendicular to a plane is just basically it's like having a pin pierce this. There's an infinite number of lines that could go in any direction in this plane, and so where they all intersect here, if this thing hits at a 90 to any one of the lines coming out of here, see this is a line here, a line right there, or we could have a line right here where they intersect, of course. Make the dot bigger. But if this thing punctures this right here, it is perpendicular to the plane because it is perpendicular to any one of those given three lines that I just drew. Okay, you could make a right angle between this line in the pen, or that line in the pen, or that line in the pen. So that's the idea here. So a line perpendicular to a plane, this is the textbook definition. Line intersects a plane perpendicular to every line on the plane at the intersection point. But visually, it's kind of like, you take a piece of paper or this whiteboard and you make the pen hit it at a right angle, and you have a line perpendicular to a plane. Last time we talked about conditional statements. Conditional statements, and what was key to a conditional statement? What did it have in it? Yeah, and then if represented the, you know, the fancy word for it? Yes, and then the then is the, okay. So, and when we get into proofs in geometry, the if part will be the given in your proof, like what you're starting with, and the then part will be what you're trying to prove. And we'll talk about how to do those two-column, paragraph, by diagram. Then if we go back one lesson, do you guys remember what inductive reasoning was? Looking at patterns, yeah. And deductive reasoning is going to be Tuesday's lesson, and there's one word that I have to define that we're going to be doing a lot of. But a biconditional statement, this is the big one today, is an if and only if statement. And a lot of the theorems that we will be proving are biconditional statements that are true. Today we're going to look at some biconditional statements that may or may not be true. What makes them biconditional is that they'll have an if and only if in it, not the fact that they're false or true. But like I said, when we get to our proofs, a lot of the theorems are biconditional. Yeah. With the sub, you're going to be working on the algebra review, those 3 pages of the packet. And if you so choose, you can wait until tomorrow to do this. So this is due at the end of the period. Keep that in mind. End of the period tomorrow, yeah. So that's what I'll write on there. I'll tell the sub there's some bookwork, what bookwork I want you to do. And then collect it at the end of the period. All right? And then the algebra review, I'm not going to collect. It's part of the packet. I will eventually when you take the test. But I'll answer questions on the algebra review on Tuesday. So if you have any questions, I'll put that down. It's pretty important. That systems of equations stuff is pretty important. You can do that. All right. This next one here, it says points D, X, and B are collinear. We're supposed to, is this asking us to write, is that true or false? Yeah, okay. And then explain it. And then explain, okay. So points D, X, and B are collinear. D, X, and B. What do you think, true or false? True. True. How do you know? We're on the same line. What about, this says, this is the symbol for perpendicular, upside down T, which you should know. AC is perpendicular to DB. It's true. How do you know? Yeah, they make a right angle. And what about the the third one on here. Angle AXB is adjacent to angle CXB. No. AXB, let me outline here. AXB is adjacent to angle CXB. Vertical. Yeah, it's false. They're actually vertical. They can't be vertical and adjacent. Not adjacent. Can't be both vertical and adjacent. All right, so this is a biconditional statement. 3 lines are coplanar, if and only if. There's what makes it biconditional right here. If and only if. So we're going to write it as a conditional and a converse. And like I said, when we get to our theorems, the conditional and the converse would both be true because it's a theorem and it's been proven. We're going to kind of walk through the steps of the same proofs that have already been done. Using our definitions and other theorems and postulates. But we can still write this as a conditional. So here's what it looks like. We just start with an if out in the beginning. If 3 lines are coplanar. If 3 lines are coplanar. I'm okay with you using numbers instead of words, whenever you can. If 3 lines are coplanar, then they lie in the same plane. And then the converse would be, and once again, since I'm using, now that I'm writing the converse, I'm going to tell you what I'm talking about in the first part of the converse. So instead of being literal here and saying if they lie in the same plane, then 3 lines are coplanar. Right? You could just put if 3 lines lie in the same plane, then they are coplanar. It should be okay to put the they somewhere else in the 3 lines in the beginning. But or you can be literal if you want. Either way. But if they, I guess we'll not be literal. If they lie, or we will be literal here, if they lie in the same plane. So we're taking the green part of that. Don't know what I'm talking about yet, but if they lie in the same plane, then 3 lines are coplanar. If they lie in the same plane, then 3 lines are coplanar. It would be okay to say if 3 lines lie in the same plane, then they are coplanar. So that's the conditional and the converse. Remember, the converse is just switching the if and the then. Switching the if and the then. Then inverse is negating it. I'll be quizzing you on that sometime for next week, but probably not Tuesday, but possibly Wednesday. This first few sections, probably the first 3 or 4 sections. Then in example 3, they're asking us to write this as a conditional. I think we have to decide if we decide it's true or not first. We write the biconditional statement. Let's see. Write the converse of each statement. Decide if it is true. If it is true, then combine it with the original as a biconditional. So first we're going to write the converse of the statement. So it would be take the then part and make it the if part. So if the line containing 2 points lies in a plane, figure out what the then is. If the line containing 2 points, it's the then, lies in a plane, then the 2 points lie in a plane. So we're supposed to decide if both the conditional and the converse are true, and if they are, we're going to write it as a biconditional. So first one was if 2 points lie in a plane. So if I stick 2 dots just in the plane, this purple plane right here maybe, a dot here and a dot here, then the line containing them is also in that same plane, the plane of this screen of the TV. Is that true?
Yes.
Yeah. What if I go the other direction? If the line containing 2 points, so that black line containing those 2 points, lies in the plane, do the 2 points have to also be in the plane? Yeah, they do. So we can write a biconditional for this. And all we do is take the red part here, the 2 points lie in a plane, and then we're going to combine it with the green part by putting in an if and only if. So if and only if, there's what makes it biconditional. And then I'm going to write the green part, the line containing them. Lies in the plane. So you're going to be asked to do that. Write the converse, then decide if both the converse and the conditional are true, and if they are, write it as a biconditional. So the biconditional is just connecting the hypothesis and conclusion with an if and only if.
That's 1 page.
It is only 1 page. Yeah. Want to see the mathematical symbol for if and only? I'd allow you to use this. It looks like this. That's the if and only. If you want to use that, you can. Recognized by mathematicians everywhere. If and only. That's the if and only. See, it still looks like an arrow going both ways. The equal sign. That's the if and only. What about the second one? Do you think is the converse true on this second one? No. The number is divisible by 5. If a number is divisible by 5, then the number ends in 0.
So no, because it could end in 5.
In 5. Like 15. So we have a counterexample. So if the number is divisible by 5, so a number like 15 could be divisible by 5. And then since it doesn't end in 0, then it's not true. So we just write the converse and then write false. And the number ends in 0. And we would say that's false. And the counterexample, yeah, it's 15. The 15 is divisible by 5, but doesn't end in 0. Yeah.